Hey guys, this is Mrs. Harbin, and after making our 3.1 video the other day, which really just walks us through the examples in the book, I was a little dissatisfied because I feel like it really didn't explain some of the important terminology that you really need to know. So I created this part 2 to power functions to kind of review what we already know about functions and make sure you're really solid with that terminology before we move into evaluating and graphing and really looking in detail at power functions. So let's take a quick review of the different types of functions that we've learned about so far. So the first type of function is a linear function, and this just looks like a straight line. It can be a straight horizontal line, it can be maybe a straight vertical line, it could be a slanted line. Slanted up, so that would be a positive slope or a negative slope. And this is the type of function that you learned about back in pre-algebra, Algebra 1. And it's written in this form, ax plus by equals c, where a, b, and c are constants and they're all real numbers. And our x and our y terms just have an exponent of 1. We're going to take a look at what some linear functions look like and see if you can identify them here in a minute. Another type of function is a constant function. And a constant function is also a straight line, and that's when f of x equals a. That's where a is a real number. All right, so you've got a straight line there. F of x equals a. So you've got a straight line through your y value, maybe at 3, maybe at 4. Notice it's not x equals a constant, because at that point we have a straight vertical line like this. If x equals 3, we get the straight vertical line, and that's not a function. It does not pass the function test. So constant functions are only straight horizontal lines going this direction, and our a has to be a real number. The next type of function we learned about was the quadratic function. And quadratic functions, when they're graphed, form parabolas. Remember, a parabola is this shape right here, and it's written in this form. F of x equals ax squared plus bx plus c. Here are our constants again, and a, b, and c are real, and a is not 0. You could have a b be 0 or even your c be 0, but a is not 0. The important thing to remember about quadratic functions is that they've got this squared term as their highest degree. So the degree of that polynomial, degree of that function is 2, and they always make this parabola shape. It could be up, it could be down, it depends on that leading coefficient, but it's always that parabola shape. And then lastly, we learn about polynomial functions, and polynomial functions form or can form curves, and they're written in this form. Oh, I don't know why f of x is in there twice, but f of x equals ax to the n. Man, I've got some typos. And then we've got another constant here times another x term here to 1 degree less, and keep on going to be a constant term. The reason that these say n and n minus 1 is because they could be, a degree of 27 if we wanted, and have a 27th term, and a 26th, then a 25th, and a 24th. Although typically we're not going to see polynomials. So while a quadratic function has those 3 terms, with the highest term being that squared degree there, the highest degree, polynomial functions are not limited by what degree they can have, and so that's why we've got that n term right here. We do need to remember that our coefficients, whatever they are, I put a, b, and c here, but whatever our coefficients are, they are real. And importantly, our exponents must be non-negative. Now, you may think, well, that kind of sounds like a quadratic function to some extent, and a quadratic function is a type of polynomial function. It is a type. So our polynomial function might have just a curve that looks like a parabola, or it might have a curve that looks like this, or we've seen all kinds of different polynomial curves in here. So a quadratic is a type of polynomial function. In this chapter, we're going to look at some other special functions, and we're going to start off with power functions. Now, the important thing to remember about a power function is that it only has 1 term. If you remember what we just said about polynomial functions, they are not limited in how many terms that they can have. Okay, quadratic function, we've got the squared term, the x term, and our constant term, although it may have less than one of those. It may have a 0 for b, so it may not have a b term or a 0 for c, but it has no more than 3. Polynomials not limited. A power function has one term, only one term. In a power function, we know the coefficient, and we know the exponent. We do not know the base. That is the variable. And in a power function, the domain is all real numbers if the exponent is positive. Power functions, unlike polynomials, can have negative exponents. Now, for right now, we're not going to deal with those negative exponents. So right now, all of our power functions are going to have positive exponents. And so therefore, the domain will be all real numbers as long as that exponent is positive. So here are two examples of power functions. And let's look at our definition and see how these fit. Power function has only one term. Check. We know the coefficient and we know the exponent. Check. We do not know the base. Check. And because this exponent is positive, we know that we will have a domain of all real numbers. Take a look at this one. It has only one term. Check. We know the coefficient and the exponent. We've got a coefficient of -1 and an exponent of 3. Check. We don't know the base. That's our x term. Check. And our domain will be all real numbers if the exponent is positive, and in this case, the exponent is positive. Now remember, a power function can have a negative exponent, but for right now, we are not going to do anything with those. We're going to get to those later, but just remember that is a power function right there. It just won't have a domain of all real numbers like we saw with our positive exponents here. So let's see if you can classify power function, polynomial, or both. What about this term, f of x, or this expression, this function, f of x equals 3x squared? Which one is it? Well, hopefully you said both. It is a power function. It is also a polynomial. It's a power function because there's only one term. One term. We know our coefficient and we know our exponent. We don't know our base. But it can also be a polynomial, because we have this term and we have a positive exponent. Okay, that would be a monomial. What about f of x equals negative x cubed? Which one is that? Power function, polynomial, or both? Hopefully you said again, both. Power function and polynomial, it would qualify as both. As long as we have this positive exponent here, it's going to qualify as both. What about this function? Hopefully you said polynomial. We know it cannot be a power function because it has more than the one term. It can still be a polynomial, however, because it does have positive exponents. And lastly, hopefully you said just a power function. It cannot be a polynomial because it does not have a positive exponent. It's got that negative exponent. So even though we are not doing any work evaluating this type of power function just yet, we'll get to it soon. And you should know that it is a power function. Let's take a look at these graphs and see if you can identify the types of graphs here. We've got 1, 2, 3, 4, and 5. Now some of these have equations with them, and so you can actually see what they are. So starting up here, we've got an example of a linear function that ax plus by equals c, or oftentimes y equals mx plus b. When we are doing it in slope-intercept form, we've got this straight line. This is our example of a constant function. F of x equals a number, real number, straight line, horizontal line. That is our constant function. Remember that a vertical line is not a constant function because it's not a function at all. Over here, we've got example of our quadratic function. You can see we've got this nice parabola here. We've got our x squared term as our highest degree, so that tells us it's quadratic. And remember, a quadratic is just a type of polynomial. And we've got several different polynomials drawn over here. We've got this one, this pink function, this green function right here, and then this nice blue quadratic polynomial function. Notice that each of these functions does look different, and we learned last chapter about why they look different. Depending on the degree, whether it's even or odd, depending on whether that leading coefficient is positive or negative. That determines how many maximum and minimum points we have, humps and bumps, we said. It determines the behavior of the tails, the end behavior of the tails. And so that's why each of these polynomials does look different. And finally, we've got some power functions depicted here. We've got x to the first degree, which is just this straight line right here. This is also known as the identity function. Y equals x is also called the identity function, and that is just x to the first degree, that straight line right there. That's when our x and y values are identical for every point on the graph. It's a power function of 1 degree, and it's also a linear function. It qualifies as both. So when x is a 1/2, y is 1/2. When x is 1, y is 1. When x is -1, y is -1. Again, that's called our identity function. Y equals x is our identity function. And then we've got two other power functions depicted here. We've got x cubed, is that blue line, and x to the 5th, which looks very similar, is this red line. Notice that what's being changed is kind of that degree of maybe degree is not the best word, the sharpness of that curve. For x cubed, it's kind of more of a gradual curve. X to the 5th, we've got closer to a 90-degree curve. Maybe you can predict what x to the 7th or x to the 9th might look like. Our curves there would get sharper and sharper. All right, let's talk a little bit about symmetry and our power functions. Okay, we've talked already, when we talked about polynomials, of something being symmetrical across the y-axis. And what that means is that what's on this side is symmetrical to what's on the other side of the y-axis. Okay, if we go to maybe 3 on our x and our -3 over here on x, we're going to get the same y value for both the positive and the -3. That's how we know that that is symmetrical. So maybe this is 3, 2, and then over here would have to be -3, 2. And that shows symmetry across the y-axis. This is what happens when we have power functions that have an even power. When our constant is greater than 0 and we have an even power. So maybe we have x squared. We would have something that looks like this. An even power, a positive constant, and we've got this symmetry over the y-axis. An odd power degree, like maybe x cubed, for example, as long as our positive is, our constant is positive and greater than 0, would look something like this. Okay, so this is no longer symmetrical with respect to the y-axis. Instead, we now have symmetry with respect to the origin. Okay, so this is symmetrical over the origin. This also has something called point symmetry. And what point symmetry means, let's say that we choose a point on the curve above the origin, maybe this point right here. All right, so we choose a point above the curve or above the origin. And if we draw a line that connects this point and the origin, and this is not going to be very straight because I'm doing this free-handed here, it's going to go through the other side of the curve and the other side of the origin, and both of these points are the same distance away from the origin. So let's say that this point is 3 units away from the origin right here. Then this point over here will also be 3 units away from the origin. And that is what we call point symmetry about the origin. And this is true of our odd power functions. They have that point symmetry about the origin. Symmetry over or about the y-axis over here on even powers, and point symmetry about the origin over here with our odd powers. So these are what our even and odd functions look like when our positive constant k is greater than 0. When we have a negative constant, like our k is less than 0, let's take a look at what happens. On our even power, it creates a mirror image on the other side of the x-axis. It flips it over, points it upside down, but the tail is going upside down now on the x-axis. And look what happens to our odd power functions when they become negative. It changes the behavior of our tails. It actually flips it over the y-axis. So what was pointing up on the right side of the y-axis up here is now pointing up on the left side of the axis. We moved our point from here to here. And the tail that was pointing down in quadrant 3 on our odd-powered function up at the top here is now pointing down in quadrant 4. So we have flipped that over the y-axis by changing that constant to a negative.